I want to start today's deep dive by asking you to do something. It might sound a little strange, but I promise it sets the stage for everything we are about to discuss.
Go ahead.
Wherever you are right now, in the car, at home, on a walk, I want you to just pause for a second, stop moving, be completely still.
Take a breath. Feel the ground under your feet or the weight of your body in your chair.
What do you feel? You probably feel, well, nothing. You feel stability. The ground feels solid, unmoving.
It feels permanent,
Ah,
safe, like the one thing you can absolutely rely on to be still.
exactly. But that feeling, that deep-seated sense of stillness, it's a complete illusion.
It's a trick, really, a beautiful trick of physics and your own frame of reference.
Because here's the reality, and our senses are completely blind to it. If you're listening to this near the equator, you are, right now, moving at approximately 1,670 kilometers per hour.
And that's not a metaphor. That's your actual speed.
To put that in perspective, that is faster than the speed of sound. You are on a supersonic joyride, and you don't even feel it.
You're riding on the surface of this massive sphere that's spinning with just immense angular momentum.
And the only reason you aren't, being peeled off the surface by a catastrophic wind is because everything else is moving with you.
The air, the oceans, the buildings, everything is locked into this perfectly synchronized high-speed dance.
It's incredible. We're hurtling through the cosmos on a spinning top, but because we're inside the system, it feels like we're sitting perfectly still.
But that leads to the question for today.
What happens if the dance stops?
Mm.
What happens if we take that 7,670 kilometers per hour and we just snap our fingers and turn the speed dial to 0?
An instant, complete halt of the solid Earth.
And just so we're all on the same page, this isn't science fiction we're talking about today. We're not just, spitballing ideas.
No, this is a rigorous simulation.
Yeah.
We're using the Eclipse Yardmaster Knowledge Core and the Planetary Disaster Modules to explore this based on hard physics.
The stakes are, well, they're planetary. Would gravity fail? Would we be flung into space? Would we even survive the first second?
This is a deep dive into the terrifying and beautiful precision of Newton's laws.
So before we break the planet, we should probably understand how it's currently working. That number you gave, 1,670 kilometers per hour, that's a huge number, but it's specific to the equator, right?
That's right. You have to think about the geometry. The Earth is a sphere, more or less, and it spins on an axis that runs through the north and south poles.
Like a basketball spinning on your finger.
Exactly like that. And if you were standing right on the North Pole, right where that finger would touch the ball, your rotational speed is effectively 0.
You're just pivoting.
You're just turning in a very, very small circle once every 24 hours. You'd never feel it. The distance you travel is almost nothing.
But as you walk south from the pole,
The circle you have to travel in those 24 hours gets bigger. The radius from the axis increases. By the time you get down to the equator, you have to travel the full 40,000 kilometer circumference of the Earth.
and you have to do it in 24 hours. That's the constant.
It's a strict timekeeper. So you just do the math. Distance over time. 40,000 kilometers in 24 hours.
Yeah.
And there's your 1,670.
And all of that motion, that spin, it carries something you mentioned earlier, angular momentum.
Yes. And this is probably the single most important concept for our thought experiment.
Can you break that down? How is that different from, say, the momentum of a car driving down the road?
So regular momentum is for an object moving in a straight line. We call that linear momentum. Angular momentum is the rotational equivalent. It's the deep-seated tendency of a spinning object to just keep spinning.
Okay.
And it is a conserved quantity in physics. You can't just make it disappear. The Earth has a colossal amount of angular momentum, a sort of rotational energy. It's stored up since its formation 4.5 billion years ago.
It's like a flywheel that's been spinning for eons.
A planetary scale flywheel. And critically, that momentum isn't just in the rock.
Right. It's in everything.
Everything. The oceans, the atmosphere, you, me, the coffee in your cup. We are all moving eastwards at that same incredible speed, all sharing in that one system of momentum.
Okay, so before we slam on the brakes on this whole system, I want to clear up a really common question. I see it online all the time when this topic comes up.
I think I know which one you mean.
People ask, if the Earth stops spinning, does gravity turn off? Do we all just float away?
It's a great question because it gets at a common misconception. And the answer is a very firm no. Gravity does not come from spin.
Gravity comes from mass.
Exactly. Gravity is the fundamental force exerted by mass. The Earth has a mass of nearly 6 septillion kilograms. As long as all that rock is there beneath our feet, its gravity will be there, pulling us down,
Yeah.
stopping the spin, doesn't make the planet vanish.
And looking at the data here, it's actually a bit more nuanced. The spin does fight gravity, just a tiny little bit.
It does. And that's because of something we call centrifugal force.
Like on a merry-go-round at the park, when you feel like you're being thrown outwards.
That's the perfect analogy. The Earth is a giant, fast-spinning merry-go-round. At the equator, where the speed is highest, that spin is trying to ever so slightly fling you off into space.
But gravity is just so much stronger.
Oh, vastly stronger. Gravity wins easily. But that little outward push from the centrifugal force does counteract gravity's pull by about 0.3%.
So if the Earth stops spinning...
That outward push disappears, vanishes. The only force left is gravity. So you would actually feel heavier.
Really? By how much?
Not a lot. If you weigh, say, 180 pounds at the equator, you'd suddenly weigh about 180.5 pounds. It's not enough to crush you, but it's measurable. You're stuck to the ground a little bit harder. Okay,
so gravity is safe. We're not floating away. That's the good news.
That is the good news.
Now for the simulation. We have two ways we can run this. Scenario A is the, let's call it the action movie version, the instant stop.
The inertia catastrophe. I like that name for it.
Then we'll do scenario B, the more scientifically plausible gradual stop. But let's start with A because it illustrates the physics so brutally.
It certainly does.
Okay, we snap our fingers. The solid part of the Earth, the crust, the mantle, the bedrock our cities are built on, comes to a complete stop. 1,670 kilometers per hour to zero, instantly. What happens to everything that's not bedrock?
Newton's first law of motion takes over. An object in motion stays in motion.
Inertia.
Pure inertia. We've applied some magical, impossible brake to the solid planet, but we haven't applied that brake to the atmosphere or the oceans.
So they keep going.
They keep going. At 1,670 kilometers per hour, instantly, you have the entire planet's atmosphere moving eastwards at supersonic speed relative to the now stationary ground.
I'm trying to even picture that. The speed of sound is around 12,235 kilometers per hour. So this wind is, what, Mach 1.3, Mach 1.4?
In that range, yes. We're talking about a global supersonic wind blast.
I've seen videos of Category 5 hurricanes, winds at 300 kilometers per hour. They shred towns. This is more than 5 times faster.
And at those speeds, air stops behaving like a gas. It's not a breeze, it compresses. It forms a shock wave. It behaves more like a solid. It would hit everything on the surface like a planetary scale sledgehammer.
It wouldn't just knock buildings over.
It would scour them from their foundations. The word we use in this simulation is scour. It's the only one that fits. Trees, buildings, topsoil, people, animals. Anything not physically part of the planet's deep crust would be sheared off and pulverized in a fraction of a second.
And that's not just at the equator. Even here, at mid-latitudes, you're still talking about speeds over 1,000 kilometers per hour.
Yes. The destructive force would cover virtually the entire globe. The only places that might be spared the initial shear would be the areas directly at the North and South poles, where the rotational speed is near zero.
But even there, you'd be watching the rest of the world get erased.
And that's not even the only effect from the wind. There's a secondary one that's just as lethal.
The heat.
The kinetic energy surge. Friction. When you have air moving at Mach 1.4 across a rough surface like mountains and forests and the ruins of cities, the friction is immense.
It would heat the air up.
It would heat the air up to furnace-like temperatures almost instantly. The entire atmosphere would become a superheated, supersonic blast furnace. The friction would be so intense it would cause anything flammable to spontaneously combust.
So it's a scouring wind and a global firestorm at the same time.
It is essentially the sterilization of the planet's surface.
And we haven't even gotten to the water yet.
Ah, yes. The oceans. This is where the true scale of the momentum problem becomes clear.
Because water is so much denser than air. A cubic meter of water is a metric ton.
Exactly. And the oceans possess that same eastward momentum. So when the ocean floor beneath them grinds to a halt, the water doesn't.
It wouldn't just be a wave.
No. The word tsunami is completely inadequate. This isn't water being displaced by an earthquake. This is the entire body of the ocean itself, continuing to move at over 1,000 kilometers per hour.
So the Pacific Ocean would just continue east and wash over North and South America.
As a wall of water, kilometers high, moving at near supersonic speeds, it would sweep across continents, scouring them clean down to the bedrock. It wouldn't just go over mountains, it would obliterate them.
And the Atlantic would do the same to Europe and Africa.
It's like taking the entire surface of the planet and putting it in a blender on the highest possible setting.
And beneath all that chaos on the surface, the rock itself would be in agony.
The tectonic impact would be unimaginable. Remember, the Earth is layered. You have the crust, the mantle, the core. If you magically stop the crust, the liquid mantle and core beneath are still trying to spin,
So you'd have this incredible shear force between the layers.
which would trigger the most violent earthquakes possible everywhere on the planet simultaneously. A crust would fracture and break apart. Global volcanic eruptions would be triggered as all that internal pressure is released. The planet might literally tear itself apart.
Okay, so scenario A, the instant stop, it's a non-starter for survival.
It's an extinction event on a scale that is difficult to comprehend. Complete and total annihilation in minutes.
Right. So let's pivot to something a little less immediately apocalyptic. Scenario B, the gradual stop.
This is the more scientifically interesting scenario because it lets us explore the long-term consequences.
So let's say some force causes the Earth to slowly break, maybe over, say, 50 years. The inertia catastrophe is avoided. The atmosphere and oceans slow down with the land. We just gently grind to a halt.
We survive the initial stop, yes, but now we have to survive the new environment we've created, and the first thing we'd notice is time itself changing.
The day gets longer.
And longer and longer. A 24-hour day becomes a 48-hour day, then a week-long day, then a month.
And looking at the biosphere data, almost all life on Earth is fundamentally tuned to that 24-hour cycle.
Our circadian rhythms, yes, it governs everything from sleep patterns to hormone release. But for the planet's ecosystems, it's even more critical. Plants need a cycle of light for photosynthesis and darkness for respiration.
So if the sun stays up for, say, 300 hours straight,
The plants get scorched. They can't cope. And if they're then plunged into 300 hours of darkness, they starve and freeze. The foundation of the food web begins to crumble.
and if we start rotating entirely, a day becomes a year.
That's right. And we should be clear about the orbital mechanics here. The Earth would still be orbiting the sun.
Right, this doesn't mean we fall into the sun. Rotation and revolution are two different things.
Exactly. The year would still be 365 days long. Our orbit is safe. But because we're no longer spinning on our axis, one day-night cycle would take an entire year. You'd have 6 months of continuous, unbroken daylight, followed by 6 months of continuous absolute darkness.
Which leads to what the simulation calls the thermal nightmare.
Right now, our 24-hour rotation acts like a rotisserie. It turns the planet constantly so one side doesn't burn while the other freezes
It distributes the heat.
very effectively. But if you stop the rotisserie,
Yeah.
one side burns. The other side freezes solid.
So, on the day side, with the sun just hanging in the sky for 6 months straight, what kind of temperatures are we talking about?
Well above boiling. The ground would just bake. Temperatures could easily reach over 100 degrees Celsius or 212 Fahrenheit. The oceans on the day side would begin to boil away, pumping enormous amounts of water vapor into the atmosphere.
And water vapor is a powerful greenhouse gas.
The most powerful. So you'd get a runaway greenhouse effect, trapping even more heat. The day side becomes a suffocating, boiling, high-pressure steam bath, utterly uninhabitable.
And on the night side?
The exact opposite. 6 months with no sunlight means all the heat radiates away into the cold of space. Temperatures would plummet to well below negative 100 Celsius. The oceans would freeze over into continent-sized glaciers kilometers thick. The atmosphere itself could begin to freeze and snow out onto the surface,
So the planet becomes a world of two extremes, half oven, half deep freeze.
with very little in between.
And there's another really strange geographical consequence to this slowdown, something that frankly blew my mind. The shape of the oceans themselves would change.
The bulge collapse. This is one of the most fascinating parts of the simulation.
So you mentioned earlier the Earth isn't a perfect sphere. It's an oblate spheroid.
Right. It's slightly squashed at the poles, and it bulges out of the equator. That bulge is caused directly by the centrifugal force of the spin, pushing the water and even the crust outwards.
So sea level at the equator is actually higher than at the poles.
It is. The water at the equator is about 21 kilometers further from the center of the Earth than the water at the poles. It's essentially a massive hill of water being held up by the planet's spin.
So if you turn off the spin,
Gravity takes over completely, and gravity wants to pull everything into a perfect sphere. That hill of water at the equator is no longer supported.
so it flows downhill towards the
It
pole.
would be the greatest migration of water in the planet's history. The oceans would literally drain away from the equatorial regions.
What would that look like?
You would see the emergence of a new supercontinent. A massive belt of dry land, thousands of kilometers wide, wrapping all the way around the Earth's middle. You could walk on the exposed seafloor from South America to Africa.
And all that water has to go somewhere,
It rushes north and south, creating two enormous polar oceans,
drowning what's currently there.
drowning almost everything. In the north, all of Canada, northern Europe, Russia,
Oh,
gone. Submerged under a new, deep polar sea. In the south, say goodbye to New Zealand, Argentina, and the southern half of Australia.
so the only land left is this new hot continent at the equator, but that's the part of the world that's boiling under a permanent sun.
That's the cruel irony of it. The habitable land moves to the most uninhabitable climate zone.
Let's go back to the atmosphere for a second. Without the spin, you lose the Coriolis effect. What does that mean for weather?
It means weather as we know it
Hmm.
ceases to exist. The Coriolis effect is what gives us our complex weather patterns. It's what makes hurricanes spin and organizes winds into jet streams.
Just without it.
Weather becomes incredibly simple and incredibly violent. It reverts to a basic circulation pattern. Air gets superheated on the dayside, rises, flows at high altitude to the freezing night side, sinks, and then flows back along the surface.
So you just have a constant, massive wind blowing from the cold side to the hot side.
A permanent gale-force thermal wind. And where that hot and cold air meets would be a zone of storms unlike anything we can imagine.
Which brings us to survival. If the day side is boiling and the night side is freezing, is there any place left to live?
There is one possibility. A thin band around the planet that separates day from night.
The Twilight Zone. Or the
Yeah.
Terminator.
Exactly. The land of perpetual sunrise or perpetual sunset. In this zone, the sun would always be on the horizon. The temperatures could, theoretically, be mild enough for liquid water and perhaps for life.
But you couldn't build a city there.
You couldn't. Because the Earth is still orbiting the sun, that twilight zone is constantly moving across the surface.
So you'd have to be nomadic.
Humanity would have to become a migrating species, constantly on the move, chasing the sunset around the globe to stay in that habitable band.
And you'd be migrating through those ferocious storms you mentioned where the hot and cold air masses collide.
It would be a brutal existence.
What about food? Traditional agriculture seems impossible.
Completely impossible. The food web collapses. No plants can survive 6 months of sun and 6 months of darkness.
So where does that leave us? How do we survive?
There's really only one long-term strategy that emerges from the data. We'd have to go down.
Underground.
Subsurface habitats. It's the only way to escape the temperature extremes on the surface.
Hmm.
A few meters down, the rock maintains a stable temperature.
And we could power these habitats with geothermal energy.
Geothermal, yes.
Oh,
And grow food with hydroponics and artificial light. It would mean becoming a civilization that never sees the sun. A species living in sealed bunkers, recycling every drop of water, every breath of air.
it's survival, but it's a shadow of what we have now.
It is. And there's one more invisible killer we haven't mentioned.
The magnetic field.
Our shield. The Earth's magnetic field is generated by the churning of the molten iron in its outer core, a process driven by the planet's rotation. It's a dynamo.
If the rotation stops
The dynamo likely weakens or shuts down entirely.
and our shield goes down.
And the solar wind and cosmic radiation come pouring in. The surface of the planet would become bathed in lethal radiation.
So even that twilight zone on the surface would be uninhabitable.
Most likely, yes. The radiation levels would be too high for complex life. It reinforces the idea that the only refuge would be deep underground, shielded by kilometers of rock.
So the spin doesn't just give us our day and night, it's actively protecting us from being sterilized by our own sun.
It is our invisible armor.
Okay. That was a comprehensive tour of the apocalypse. Let's bring it back to the real world. Probability. Could any of this actually happen?
The short answer is no, absolutely not.
And the long answer.
The long answer is the law of conservation of angular momentum. It's one of the fundamental rules of the universe. You can't just destroy that much rotational energy. You can only transfer it to something else.
So you'd need a break, a planet-sized break.
You'd need a collision. An impact from another planet-sized object applied with impossible precision could theoretically stop the spin.
But if we were hit by a planet-sized object,
The spin would be the least of our worries. The impact itself would vaporize the oceans and melt the crust. The game would already be over.
so the thought experiment is just that. It's physically impossible for the Earth to just stop while we're still here to notice.
Correct, but the Earth is slowing down.
Right, because of the moon.
Exactly. The moon's gravity pulls on our oceans, creating the tides. That tidal bulge creates friction against the rotating Earth, and that friction acts as a very, very gentle brake.
How gentle are we talking?
We're losing about 1.7 milliseconds from the day every century.
Milliseconds per century. Okay, so not something to worry about.
Not in our lifetime or in the lifetime of the human species. The sun will expand and engulf the Earth billions of years before the planet ever slows to a complete stop.
So this deep dive, it's not a forecast, it's a lesson.
I think so. It's a lesson in cosmic mechanics. It leads to a more philosophical reflection, really.
It forces you to confront that illusion of stillness we started with.
It does. We equate stability and safety with stillness. We want solid ground. But this experiment shows us that our actual stability, our climate, our oceans, our very existence depends entirely on constant, violent motion.
If the Earth were ever truly still, it would be a dead world.
Motion is life. The spinning generates our shield. The rotation distributes heat. It gives us the rhythm that drives all of biology. We are living in this incredibly narrow Goldilocks zone of motion, not too fast, not too slow.
It's a profound thought. We are surfing on this razor's edge of cosmic chaos, and we have the luxury of calling it a peaceful afternoon.
It certainly puts things in perspective.
So to summarize our journey, we started with a simple question about standing still and discovered that true stillness would mean supersonic winds, boiling oceans, a sterilized surface, and the end of everything we know.
It confirms that reality is often deeply counterintuitive. That peaceful sunset you watch is actually a view from the deck of a spaceship spinning at incredible speeds.
And I think that's the thought we should leave everyone with today. A final reminder of where we are and what's really happening, even when it feels like nothing is. We live on a planet moving at thousands of kilometers per hour, orbiting a star at 30 kilometers per second, inside a galaxy racing through space, and yet we call this stillness.